Can we find ways to determine the existence of periodic orbits without all this computation? Yes, but it's not super easy. So if we have an autonomous system with f and g continuous with continuous first derivatives in a domain D, we know that a closed trajectory, that means something that closes up on itself, must enclose at least one critical point. That means that if you have a periodic orbit, inside the area determined by the periodic orbit, you have at least one critical point. On top of that, if there is only one, not more than one, you cannot have a saddle. That means it must be either asymptotically stable or asymptotically unstable. It cannot be this middle ground in which some things are drawn towards it and some things are drawn away from it. On top of that, if you have a domain that is simply connected, so it doesn't have any holes, and if the derivative of f with respect to x plus the derivative of g with respect to y do not change sign in this domain, then we know that there is no closed trajectory fully inside this domain. In a certain sense, what we're computing is how things are flowing away. And what we notice is that they're always flowing in the same direction, roughly. That means that you cannot close things around because you are constantly pushed in the same direction. There is also another theorem that states that if you have f and g continuous with continuous derivatives in a domain D, and then you take a smaller domain D1, such that there are no critical points in D1, nor on the boundary of D1. If there is a solution that stays within D1 for all times bigger or equal than T0, then either it's a periodic orbit or it approaches a periodic orbit as t tends to infinity. Remember that we know that if we have a periodic orbit, there is no critical point, there has to be a critical point within it. But we're also asking no critical points to be within D1. That means that D1 has to be donut shaped. We are not requiring it to be simply connected because it cannot be simply connected. We're requiring D1 to be a donut such that the boundaries are as clean as possible. And what we want is that in this donut, something comes in, one specific solution comes in and never leaves ever again. But because there is no critical point, this solution cannot be going to a critical point, so it must be going to a periodic orbit. So we have the solution that enters D1 and stays in it. So either it is a periodic orbit or it goes towards a periodic orbit. Notice that if you have the opposite situation, that means everything moves away from D1, then reverting time can give us this again. Another way of looking at this is that we have D1 that is donut shaped, roughly, a very squished donut possibly, but a strip that closes back on itself. We look at the interior boundary and the exterior boundary. And we want the direction field on this boundary to either constantly go inward and out or outward. So what we want is that on the gamma 2 boundary, the inside, everything goes towards D1. And everything on gamma 1 goes towards D1 as well. This is another way of saying that anything that enters D1 stays in D1. We could have points in which the direction field is tangent to the boundary of D1. If all orbits are trapped inside D1 and there are no critical points in D1, then the only option is for it to be a periodic orbit. Notice how in this case it's easy to see that if we're flipping all directions, that means that considering the donut D1, everything is leaving D1 in both directions. Flipping time would also give you a periodic orbit. That means that there is a periodic orbit. The only difference between the two situations is the stability. If everything is moving towards D1, then the periodic orbit inside must be stable. If everything moves away from D1, then the periodic orbit inside it must be unstable. Let's look at an example of a periodic orbit in a more complicated system. This is the van der Pol equation. It's u second minus mu times 1 plus u squared times u prime plus u equal to 0. And we are expecting mu to be bigger or equal than 0. If mu is exactly equal to 0, well, the equation simplifies to u second plus u equals 0. And we know we have periodic solutions. So let's consider mu positive. We change our system into a ODE system. So we have x dot equals y and y dot equals minus x plus mu times 1 minus x squared times y. The only critical point is again 0, 0. And when we do the linearization, we find out that, well, the eigenvalues depend on mu in a quite strong way, because it's 1/2 mu plus or minus square root of mu squared minus 4. So for mu squared minus 4, smaller than 0, we have an unstable spiral. For mu squared minus 4 positive, we have an unstable node. So in the first case, we're limiting mu between 0 and 2, so we have an unstable spiral, and for mu bigger than 2, we have an unstable node at the origin. We can change to polar coordinates, and then we have dr dt equals mu times 1 minus r squared cos squared theta times r times sin squared theta. If r1 is very small, so we're considering a little ball around our critical point 0, 0, then we have r1 that we can approximate by mu times r times sin squared, because r squared is very small, so 1 minus r squared cos squared theta will be pretty much equal to 1. And r1 dot, being mu that is positive times r that is positive times sin theta squared, it's bigger or equal than 0. It's equal to 0 only for theta equal to 0 or theta equals to plus or minus pi. So what we know is that if we're looking at a small ball, around y equal to 0 we're going vertically, but in all other directions we're going outward towards our donut shape. So now we're considering R2 being big, so we're really creating this donut, and we're hoping to find the existence of a periodic orbit between R1 and R2. So for R2 big, then we go back and we look at our system, and we have that mu is positive, r sin squared theta is positive. We would like 1 minus r squared cos squared theta to be negative all the time. So we can prove that everything is entering our donut shape. But this is not true, because R2 is very big, so usually 1 minus R2 cos squared theta will be negative because R2 is very big. But when cos theta is too small, or even 0, then the fact that it's multiplied by something very big doesn't matter. So our block 1 minus r squared cos theta is negative unless cos squared theta is almost 0. Then that block is going to be positive again. That means that R2 prime doesn't have a clear sign as we would like it to have. There are 2 points in 2 areas in our graph, in our faceplate, in which we can't guarantee that things come in. Actually, we can guarantee that things go out. This is too hard to solve analytically with the level we are developing on this course. So we're going to try to develop it in another way. We're going to try to gather enough numerical evidence to convince us that most probably there is a periodic orbit. This is not a proof, so we cannot prove that there exists a periodic orbit. We can just gather enough plots and show enough data to go like, the possibility of it being something else than a periodic orbit is extremely slim. So let's look at MATLAB code.